everyone, I'm Xiangyu. In this session, I will talk about the reinforcement learning based recommender system. So as Dr. Tang and Wenqi introduced before, we receive a lot of information every day from different platforms. So the recommender system is a kind of way to help us to locate the information we want. So the task of a recommendation is actually it want to suggest the item that can best match our preference. So for typical recommender systems, we will do two things. So the first is we want to learn the user's preference from his profile. For example, your gender, your age, your browsing histories. And the second thing is according to user's preference, we want to suggest the item that can match the preference. So the second step is more about how to generate recommendations. So although there are many solutions for these two steps, I think there are still some challenging problems about the recommendation policies. So because we found that most recommender systems consider the recommendation procedure as an offline optimization and only focus on the short-term reward. So for example, in this case, when we use matrix factorization, we can build a user model offline, and once the model is built, it is fixed when we launch it online. So that's why it is an offline optimization. And once we found that the user may like this book, we will immediately recommend this book to the user, but we don't consider the long-term influence. So, but following this way, actually, there are some obvious disadvantages. So first, we will overlook the real-time feedback from users because once we build the user model offline, it is fixed when we launch it online. And the second challenge is that, as I just mentioned, typically they focus on the immediate reward. So basically, we want to guarantee once we recommend an item to a user, the user will be likely to buy it. But we don't consider the long-term influence on the user experience. So what's the disadvantage of this policy is you will get things more and more similar. So for example, last year is the election time, and one day I watched some debate between Biden and Trump, and the second day I got some recommendations about the debates. I feel excited because it's just the second day, so I give some positive reward. But after a few days, I get more and more. I feel really bored. So if you always follow this kind of short-term reward, you will get more and more similar recommendations, and eventually there is no surprise at all. So why we want to introduce reinforcement learning for recommendations? So in reinforcement learning, there is an agent and the environment. So the agent will take some actions and the environment will give some reward. And of course, because the reward, the agent's state will change. So through the interaction with the environment, the agent can learn to take the best action to get the optimal long-term reward. So, okay, this is the basic idea of reinforcement learning. So basically, there are three groups of reinforcement learning methods. The first is the value-based method. This group learns the value functions of the actions and then takes the action with the optimal value. The famous algorithms such as DINA, Q-learning, SASA, and the DQN belongs to the value-based models. And the policy-based method directly search the policy space and learn the probability of taking the actions, and then sample the action according to these probabilities. And finally, the actor critic and its variants incorporate both the value-based and the policy-based RL methods. The policy structure is known as the actor because it's used to select the actions. And the estimate value function is known as the critic because it judges the action made by the actor. So when we introduce reinforcement learning for recommendations, it mainly has two advantages. The first, the recommendation policy will be updated continuously according to users' real-time feedback. For example, if you purchase an item, we will give a positive reward to the system, and the system will reinforce this kind of recommendation policy. But if you skip the items, we will have a negative reward. So basically, the system will try to avoid this kind of recommendation policy. So this is one advantage of reinforcement learning based recommendations. And the second challenge is actually when we use reinforcement learning, we consider more about the long-term reward. So for example, we recommend something to you. Probably you will buy it and you will stop this session. There is no following up. But if we recommend an iPhone to you, probably you will also buy the case, buy the charger, buy the earphone in this session. And when we use reinforcement learning, basically we try to maximize this kind of long-term reward from the users. So this is the outline of the papers we will introduce, and we have three groups. One is reinforcement learning-based recommendations in single scenario, and another is for the multiple scenario, and the third group is the online environment simulator. And finally, we will introduce
这是任务啊，
tools. Could you turn off your
借水果啊。
Okay. And finally, we will introduce two survey papers. Okay, let's get started for the first paper. It's the deep reinforcement learning for page-wide recommendations, which is published on the RecSys. So since in reinforcement learning, we consider the interactions between the users and the system. So let's look like how does a real world interaction look like. So in a typical interaction, the recommender system will recommend a page of items to the user. You can just imagine in Amazon, and then the user will give feedback. He can click, he can purchase, and so on. And the recommender system will update its policy according to the feedback, and then recommend a new page of items, and so on, until the user terminates this session. So to capture this interaction, actually there are several challenges. The first one is since the user is continuously providing the feedback. So that's why actually we need to update our policy according to this real-time feedback. And the second thing is nowadays in a real world recommender system, they typically recommend a page of items as a whole. So how can we recommend how can we recommend a page with diverse and complementary items? So why we need a diverse and complementary page? Because we try to increase the chance that the user will click or purchase on this page. So for example, if we just provide a lot of cell phone in one page, I don't think this is a good way because actually the most cell phones are exchangeable to each other. So that's why we need to provide the diverse and complementary items. And also, because each time we recommend a two-dimensional page of items, this is different from the ranking in a one-dimensional list. So the third challenge is how to put the items properly in the page. So this is more about the item display policy. And another question is, can we address these three challenges by reinforcement learning at the same time? So then the page-wide recommendation model is proposed. So before I introduce the detail of the framework, I would like to introduce the reinforcement learning architecture they use. So in this paper, they use actor critic architecture. So different from traditional DQN DeepQ networks, the actor critic can handle the dynamic item space and it can reduce the training time. So in the page-wide recommendations, they use the actor critic architecture. So the next question is how to design the actor and the critic. So I will introduce the two components in details. So here is the structure of the actor. It contains two parts. One is the encoder. So basically, they input the previous pages they have done, and we output the embeddings of current user's preference. And for the decoder, we input the user's preference, and we will predict the next page of items. So that's the two part of the actor. I will introduce layer by layer. So the input of the encoder are the information of items in a page. So for each item, we have its identifier, which is unique for each item. And we have the items category because we want to generate diverse and complementary items. And we also have the user's feedback because we want to capture users' interaction uh, in one page. So we transform this information into embeddings, and then we concatenate these three embeddings as the item embedding as a whole. And then we place the item embeddings at the original location in the page, and we can get a two-dimensional page matrix. And the next question is how to learn the spatial pattern to put items in a page. So we can find that actually the two-dimensional page matrix is similar to an image. So we can consider the item embedding values as the pixels. And so we introduce a CNN layer to learn the spatial pattern of items within the page. And next, we use the GRU with attention layer to capture user's preference among different pages. And finally, the encoder will output the embedding of user's current preference. So this is the detail of the encoder. So for the decoder, given the embedding vector of user's preference, we aim to generate a page of items. So this is also a matrix. So it aims to address two tasks. One is to generate a set of items, and the second is to put the item's property in a page. So then the challenge is, can we address these two tasks at the same time? So the solution is using a deconvolutional neural network. So this is an inverse process of what a standard CNN does. So it can recover an image from an embedding vector. So that we can use DCNN to generate a page matrix from the embedding vector of user's preference. So by using DCNN, the decoder can generate next page of items and learn how to put them in the page by the same at the same time. And for the critic, it takes the user preference and a page of items and aim to predict the Q values. So here, a higher Q values means the page of items can lead to a larger long-term reward. And according to the Bellman equation, the evaluation of current Q value should equal to the current reward plus the Q values of next state action pair. So this is the page-wise recommendation paper. It can update the recommendation policy based on users' real-time feedback. It can optimize the long-term reward, and it can learn how to put the items in a page. Next, I will introduce the second paper, the recommendation with negative feedback via paired deep reinforcement learning. So most existing recommended system consider more about the items that the user provides positive feedback, such as click or purchase. By learning this positive feedback, we can learn what user may like. But why we want to capture the negative feedback, like users skip or the leaving behaviors? This is because the negative feedback shows what user may not like. And by incorporating this negative feedback, we can avoid the bad recommendation case, such as recommend a skirt to a male user. So capturing the negative feedback is quite challenging. The one reason is the number of negative feedback is much more than the positive ones, but we don't want the negative feedback bury the positive ones. And another reason is the user's sorry. So another reason is users' negative feedback may not because user dislikes the items, That may be because users don't pay attention or other reasons. So how to identify the items user really don't like is another challenge. And finally, this weak and wrong negative feedback can introduce noise, which also downgrades the recommendation performance. So in this paper, they aim to solve these three challenges. So this paper first designed a novel DQN architecture. So the input layer and the first few layers of the network are separated to two parts. One part is the positive states, which are learned from the recent click or the ordered the items with the positive feedback. And another input is the action, which is the potential item to recommend. And another part is the negative state that learn from the items with negative feedback. And also we have the actions. So the intuition of this design is to recommend an item that is similar to the item with positive feedback, but this similar to the item with the negative feedback. And they also use the RNN with GRU to capture users' sequential behaviors. So this is the architecture part. And also to handle the weak and wrong negative feedback, they found that the recommended system often recommend items belong to the same category, such as the cell phone, and the user will click or purchase a part of them and skip others. So this paper proposed a novel regularization term. It maximizes the difference between the Q values of two similar items, but they have different feedback. So this partial order can help to identify the items that the user really don't like. So this is the second paper. It designed a novel DQN architecture and a regularization term, which can efficiently capture users both the positive and the negative feedback for recommendations. Then I will introduce the third paper, Deep Reinforcement Learning Framework for News Recommendations. So the major novelty of this paper is it proposed a effective iteration method. So the traditional iteration method, such as random iteration, it will harm the user experience in a short term. But another traditional iteration method is multi-embedded method. They have the same issue and they have a large variance and they take a long time to converge. So this paper proposes a effective iteration method. So it has two neural network, the current network Q and the explorer network Q tilde. So the steps are they first get recommendations from Q and Q tilde, and then they probabilities could interleave these two lists and get feedback from users and compare the performance of these two models, two networks. And if the Q tilde performs better, we will update Q toward the Q tilde. But if the current network Q performs better, we will keep it. We don't update the parameters. So this is the effective iteration method of the DRN paper. So that's the papers for recommendations in the single scenario. Next, I will introduce the papers about the recommendations in multiple scenarios. Okay, the first paper is whole chain recommendations in CIKM last year. So in real-world recommender system, users often sequentially interact with multiple scenarios in one recommendation session, and the different scenarios have different objectives. For example, a user usually start a recommendation session by browsing the item in the entrance page. So in the entrance page, it suggests the diverse and complementary items according to users' browsing history. And in this page, the user can skip the recommended items and continue browsing the new recommendations. And he can also go to the item detail page if he click one item. And in the item detail page, it shows more details of the clicked item. And the agent in this page generates a set of recommendations related to this item. And in this page, user can go back to the entrance page, or he can go to another item detail page if he click on items. And also he can click the item, he can add the item into the shopping cart and go to the shopping cart page. So from this example, we can find that there is a sequence of related scenarios, and the different scenarios have a different objective. So optimizing only one recommended agent for all the scenarios will overlook these different objectives. So another solution is separately optimizing each recommended agent for each scenario. However, this design also have some disadvantages. So first, it will ignore the sequential dependency of user behaviors among different scenarios. And the second, if we optimizing each agent for each scenario, it will only use the user behavior data of this scenario and ignore the data from others. And the third, the separate optimization of one scenario will only optimize its own objective, but this may negatively influence the overall performance of the whole recommendation session. So in this paper, they formulate the recommendation task in the multiple sequential scenarios as a whole chain recommendation problem. And they leverage the multi-agent reinforcement learning to jointly optimize all the recommendation agents. So in this framework, the agents are sequentially activated to capture users' behavior in different scenarios. And all the agents share the memory of the whole user behavior data. And all the agents work together to optimize the overall performance of the whole recommendation session. And they design a actor critic framework. So here, each actor is a recommended agent in one scenario, and the global critic control all the actors and enable them to work together to optimize the overall performance. So they use the off policy method to optimize the framework based on the offline user behavior data. So take the user in the entrance page as an example. So when the agent recommend an item, the user may take three types of behaviors. So the first, he can click the item, he can skip the item, and then the agent of the of the entrance page will continue to generate the next recommendations, and this will lead to a non-zero Q value. And second, if the user clicks the recommended item, the agent of the entrance page will receive a positive reward, and then the user will go to the item detail page, and then the agent of the item detail page will generate the next recommendations, and this will lead to a non-zero Q value. And finally, if the user leaves the platform, the agent of the entrance page will receive a negative reward. And for the other scenarios, they have the similar analysis. And in this framework, they use the model-based reinforcement learning to estimate the user behaviors. This can reduce the requirement of training data amount, and it will perform more accurate optimization of the Q functions. So this is a deep chain model, the whole chain recommendation model. It can capture the user's sequential behavior in different scenarios and optimize the overall performance of the whole recommendation session. Next, I will introduce the Triple W paper, Learning to Collaborate, Multi-Scenario Ranking via Multi-Agent Reinforcement Learning. So this is another, actually is another model for the multi-scenario recommendations. So the model has a centralized and a global critic model to evaluate the overall reward, and a communication component is used to generate a message that share among the actors. And the message actually is it encodes the historical observations and actions, and can be used to approximate the global state of the environment. And each actor network represents an agent, and it will receive its own local observations and a communication message that makes private actions. And this is a detailed structure. So the centralized critical network estimates the action value function, and which indicates the future overall reward when taking actions upon the message ht minus one and the observations ot. And the actor network output a deterministic action with the given message and the local observation as the input. And the message are optimized, are updated by the communication component. It takes the input, take as the input the observation OT and the action AT. So that's the second paper about the multi-scenario recommendations. And next, I will introduce two papers for the one is jointly learning to recommend and advertise in KDD, another is deep reinforcement learning for online advertising in recommender system. So in a real-world recommender system, besides the normal recommendations, we also have advertisement, right? Such as in the Amazon, we have sponsored product. So if we show this product to the user, the advertisers will pay for this advertising impression. So the goal of online advertising is to maximize the revenue from advertisers. So to achieve this goal, we should assign the right advertisements to the right user at the right place. Some efforts have been made to develop a reinforcement learning based online advertising techniques. But however, most existing RL works, they only focus on the advertising revenue, but they ignore the negative influence on user experience. So actually, in a typical recommender system, the recommendations and the advertisements are optimized by two teams. They have different goals, they use different models, so it usually has suboptimal overall performance. So for example, if we display too much advertisement, we can have a higher advertising revenue, but the user will be mad because they have bad experience. But on the contrary, if we show fewer advertisements, the advertising revenue will go down. So my research tried to design the new method to jointly optimize the advertising revenue and the user experience. So for example, in the KDD papers, we built a two-level reinforcement learning framework to jointly optimize the overall performance of the recommender system and the advertising system. So the first level is a recommender system. So upon a user's request, the recommender system captures users' preference from his historical behavior and generate a list of recommendations that best match users' preference. So the recommender system aim to optimize the long-term user experience or engagements. So the challenge is actually it need to select a subset of item from a large item space. So this has a large computation cost. So we leverage cascading DQN for the recommender system. It can generate a list of recommendations by sequentially selecting items in a cascading manner. So the cascading DQN can reduce the combinatory complexity of selecting a subset of items from the large candidate set to the complexity of k times n, where n is the number of candidate items and k is the length of the recommendation list. And the second level is an advertising system. So it inserts advertisement into a given recommendation list, and it needs to make three decisions. So first, whether to insert an advertisement into the current recommendation list. And if yes, it also needs to decide which advertisement and where to insert. So the goal of advertising system is to jointly optimize the advertising revenue from the advertisers and minimize the negative influence on the advertisement, the negative influence of the advertisement on the user experience. So to make these three decisions, we propose a novel DQN architecture. So the input is a state action pair. So the state include the historical recommendations and the advertisement, the contextual information, and the recommendation list generated by the recommend system at the first level. And the action is the embedding of an advertisement, which is so this advertisement can represent the decision tree to select the optimal advertisement. And the output are the Q values of all locations. So this solves the decision two, which location is optimal. And to solve the first task, we add a special unit at the output layer, which is the Q value of not inserting an advertisement into the recommendation list. So when this Q value is the optimal Q value, we will not insert the advertisement. So this is the framework we can simultaneously make the three decisions. And finally, the target user will browse the mixed list of recommendations and advertisement and provide the feedback. And according to the feedback, the recommend system and the advertising system will update their policy and generate the next list for the next user request. So the advantage of our model is actually compared with the two conventional DQN architecture. It can only evaluate the Q value of one level of actions. Our model is the first individual DQN architecture. It can evaluate the Q values of multiple levels, such as in our paper, we have the we will select the optimal advertisement, the optimal location, and whether to insert these three levels. Also, it's worth to note that to compare with the classical DQN in the figure B, it requires the A times L, the forward propagations. The our architecture only need A times. So this jointly, this is the KDD paper that jointly optimizes the advertising revenue and the user experience. And next, I will introduce the online environment simulator. So as I just mentioned, the reinforcement learning-based recommendations are highly depends on users' real-time feedback. So the most practical way is the online A/B test. So in this way, a new recommendation algorithm is trained based on the feedback from real users, and then its performance is compared with the current recommendation model working online. However, we think online A/B test is inefficient and expensive. So there are three reasons. First, it usually takes several weeks to collect the sufficient data. And the second reason is actually a lot of engineering effort are necessary to develop, to deploy the new algorithm online. And finally, the online A/B tests often lead to bad user experience because when we deployed a new model online, its parameters are randomly initialized. So because these three reasons, we cannot quickly train and test a new RL-based recommendation model by the online A/B test. So in this paper, they built a user simulator based on the user's historical data, and it can generate real-time feedback like real users. And then we can use this generated feedback to pre-train and evaluate the new recommendation algorithm before we launch them online. So, but however, simulating the user's real-time feedback is challenging. So one is actually the underlying distribution of the item sequence is quite complex in the historical data. This is because the large amount of items in the practical recommender system. And the second challenge is actually to learn a robust simulator. We need a lot of historical data for each user. But in the real world system, the data available to each user is usually limited. So to tackle these two challenges, we propose a user simulator based on GAN framework. So here, the generator aims to learn the item distributions from the user's historical data, and then generate fake items that are similar to the real ones. And the discriminator want to distinguish the real and the fake items at the same time, and it aims to predict the type of user's real-time feedback on the items. I think I should skip some slides. To validate the performance of the user simulator model, we studied the performance of training reinforcement learning recommender system based on our simulator. And we use the reward of a session as the metric to evaluate the model training. And we have two baselines. One is directly training a reinforcement learning recommender system based on the historical data. And another is training the system up on the IREC-GAN, which is also a simulator, user simulator. And we can find that our model convert to the similar reward with the one up on the historical data. And our model is more stable than the model based on the IREC-GAN. So this observation means that the model can take place the real users to train the RL-based recommender systems. So there are also some existing user simulation models, such as the REC-SIM, which uses the dynamic Bayesian network, the RECO-GEM, which is based on the banded model, and the GAN-PW and the virtual Taobao, which is based on the imitation learnings. And please refer to their papers for more details if you are interested. And finally, there are two survey papers to summarize the fundamental and the recent advance of reinforcement learning for the recommendations. The first paper is written by us, and it's published in the 2019. And in this year, there is a new survey. It's just uploaded to the archive. So in conclusion, the RL-based recommender system has two advantages. So first, the recommendation policy will be updated continuously according to users' real-time feedback. And the second advantage is actually when we use reinforcement learning, we consider more about the long-term reward.